All right, so welcome everyone to the New Year's First Fridays, and I want to turn this over to my colleague Tom Nania, who's going to introduce our presenter today. Tom?
Well, so today we have the pleasure of hearing from Raffaele on Malvermi on his experimental investigation of violin bridge admittance and its relation to construction parameters, um, case studies on the Cremonese violins. And so, Raphael, thank you for sharing your work today. I've had the pleasure of knowing Rafa for about 4 years after meeting at the Mondo Acustica gathering in Cremona, where I had the pleasure of visiting his lab. And Raphael joined the image and sound processing group at the Politecnico di Milano, Italy, university as a PhD student in 2019, where he worked on a joint research project between the Department of Electronics, Information, and Bioengineering at the Department of Mechanical Engineering, based at the Musical Acoustics Lab in Cremona, Italy. Since 2022, he has been in charge of the research and didactic laboratories as a technician, taking care of scientific collaborations with the Museo del Violino, UNESCO office, and violin makers in Cremona. His main research interests are related to vibroacoustics and musical acoustics, with a specific focus on violins and stringed instruments. And so, hand it over to Raphael, and thank you again.
So thank you very much, Tom. I just want to thank you again, Fan and Tom, for the invitation at the seminars. Um, I I would say that like the title is somehow um, like leading also an intention. I thought that today was that's the first time I actually attend one of these seminars. I followed a few about the registration that there are the recordings that are shared in YouTube. So I know you know already a lot about vibroacoustic measurements, violin bridge admittances, and also radiation measurements. So the idea of today is, let's say, having the chance to talk about a bit of the Cremonese context and our lab, and maybe just share some of the research questions that I experienced through the years, and they're about how to manage like measuring violins throughout years. As Tom already anticipated, I'm in the lab of the Musical Acoustic Lab in Cremona from starting from 2019, so it's about 6 years now. The Musical Acoustic Lab is part of a larger group, research group in Politecnico di Milano, which is the Image and Sound Processing Lab. And actually, as you can see, I've just draft some of the activities that this group does, and they are like quite varying in the fields. So, but everything is more related to as a common origin, which is like telecommunication signal processing. So the idea is to be like telecommunication engineers applying our knowledge in many different applications. And in particular, I'm in the Musical Acoustic Labs, which is actually inside Museo del Violino in Cremona, which is an institution which collects some historical violins and take care of the divulgation and dissemination of violin making, not only Cremonese in general, but like making techniques and their evolution during centuries. And the idea of the labs is to somehow collaborate with all the realities and context is that are present actually in Cremona. We have a lot of like actors involved in this. What we do there is uh, actually dealing about acoustics. So I just put a bit of pictures of the activities that we do there, which are like inspection of musical instruments through 3D laser scanning, vibration measurements, which are done on prototypes, so on violins that are typically offered by violin makers to do some tests. But also there's the possibility, we had the possibility to measure also historical violins from Stradivari and Amati that are collecting in the museum. I must say, not in the way that you can see in the picture, that's for sure, but in a more like conservative and protected way. But we also had some chance to measure and have the support of like musicians to try to capture the sound of violins while playing, which is a very interesting place and task to try. I was saying the context is very wide. There are some actors that I've listed here. So our lab is in collaboration with another university, and while we are dealing about acoustics, they are more dealing with the chemical treatments, so varnishes, primers, aging, and this is the chance to collaborate and try to join the knowledges. And we did also some publications together. For example, one publication was trying to understand which is the impact of primers, which are typically the chemical treatments that are due to prepare the wood before varnishing, to the vibration of the violin. So other universities, Museo del Violino, which support us in trying to do measurements in historical violins, and also there's in Cremona a UNESCO office because Cremonese violin making was considered one of the UNESCO immaterial heritage. And so there's also like a process of like safeguarding programs, which are activities programmed to do dissemination, to create knowledge around violin making using the Cremonese style and understanding the history, see the techniques, and so on. So there's a lot of networking. My experience in these 6 years was having a lot of collaborations with people interested in musical instruments, but with different point of views. And that was very interesting because everyone uses different terminologies, see this instrument in a very specific way. And sometimes it's very useful because you understand how to look at, let's say, engineering stuff in a new way. And in Cremona, we have not only like the laboratory that is the Musical Acoustic Laboratory, but we have also didactics. We have a master degree in music acoustic engineering, where our students can try different experiences and gain different competencies. And in our lab, we can test and try to do a bit of experience in violin making with different ways, not only like with the workshop, but also with 3D printing and numerical modeling and CNCing. We can do acoustic measurements. Our students can gain a bit of experience in radiation measurements, acoustic measurements with microphones and speakers, and also a bit of music editing. And this is very good for us because actually we have a lot of collaboration also with students that can do projects, that can attend laboratory session, they can do their thesis work and help us in doing research. So my idea today is to talk about two cases in which I dealt with bridge admittances measurements, and then with the help of some actors, which I will acknowledge then, we faced two different let's say, approaches to look at the data and try to understand something. But let's talk about first about the data. So with data, I mean this. I mean violin bridge admittances. As you know, this is, I think, a shape that you saw a lot of times, and you commented a lot of times. In during these years, I had the chance to measure several violins. I will describe then which protocols we use to do the measurement of violin bridge admittances, and the idea of collecting instruments was to make the laboratory open to people willing to know something about their violins. So that could be violin makers from Cremona or outside Cremona, the Museo del Violino collection, other actors interested in that. So this is like the collection of data that we have. That I put intentionally all together, uh, just because I like the idea of complexity that this graph shows. These bridge admittances come from violins that show a lot of variability. They come from different makers. They are made in different time periods. The different shapes were used to make the violin box. A different material were chosen. Different aging process, different chemical treatments, varnishes, but also different setups. At the end, different bridges, different strings, and all these factors somehow have an impact on this measurement, on the final measurement. And the measurement is essentially this one. So bridge admittances are a way, a compact way to represent which is the energy associated to each frequency when this is transferred through the bridge to the violin box, starting from the string. In a way, it's like a filter that is, from the point of view of the strings, is a filter that is able to shape the harmonic content of the note that the musician is playing. And it's a compact description of all the resonances and all the physical phenomenon that are investing and involving the violin. As you can see, we have a pretty, let's say, handmade measurement rig. I've seen Joseph Curtin, which is way better than this, and but actually it was more like a didactic challenge to try something really low cost and see which are like the element of a measurement rig that can somehow impact and infect the measurement. Typically, the principles of measuring violin bridge admittance are the ones that I tried and listed on the left. So the violin must be free to move. So we use typically suspension using rubber bands or nylon strings. We try to avoid several contact points for the suspension. And then we use hammer impacts. Hammer impacts are done with instrumented like the with hammers, like the one in the pictures. There's a pivot there that can be tuned and moved to the right position, and this provides a way to do repeatable hammer impacts through the bridge. We put the excitation point on one side and we measure the vibrational response of the whole body through the bridge on the other side of the bridge. Actually, that's one of the several bridge admittance that you can measure there, in the sense that depending on the direction you are exciting and acquiring the vibration, you can have more curves, more measurements of the bridge admittance that can tell the response of the violin box, and somehow highlights different effects that are going on in the violin throughout the process. This is a very simple way to measure, fast, and also easy and not invasive. And that's why we could use them also uh, on the collection of historical violins, because actually we just put the violin on the measurement rig. That means we do the impacts and that's it. But again, it's a good way to see actually from the vibration here, if something is happening, if there are some variability, and you can see there's a lot of variability. So, like the first question is, when you collect blindly all these kind of violins for 6 years, then what you can do, how you can sort out the mess that is going on. And that was quite an issue because I was trying to understand which can be actually relevant in this measurement and which cannot be considered relevant, or what is really varying depending on interesting variations that we want to check and somehow validate, and which one not. What we tried to do was to find some, let's say, descriptors or some elements to quantitative observables that can somehow tell us what is going on in different ranges of these measurements. Of course, signature modes are widely used. We always name them, and they are one of the mainly sound radiators, and so it's better to track them. And in this case, we have four of them. I just took and borrowed some pictures of known papers from Jim and Colin. They put here just for as an example of how the violin box vibrated these signature modes. A0, which is the Helmholtz mode, the cavity air mode, and then we have the cross roboidal, the breathing mode, and the bending mode, in which the whole plates are synchronously involved in the vibration. But then after 2 kHz, we have the energy is more associated to the vibration of smaller objects, and in particular the bridge. So we can somehow extract quantities from these signature modes, which are like the mode frequency, mode amplitude in the curve, the Q factor, which tells us about something about the damping and the temporal duration of the vibration. And then we can find another way to represent the higher frequencies when modes are not distinct enough to be recognized, and we want something more, let's say, more compact and more able to also deal with the statistical, let's say, variability that there is at a high frequency. So one way we try to use, there are some in the literature. Um, One way was to look at the energy of the curve. So understanding where the energy is distributed. If more in the low frequencies, more in the high frequencies, which is the ratio between them. And we use this curve that you can see on the bottom of the slide, which we call the relative power curve, which is actually a way to see at any frequency, which is the amount of energy that is from the first frequency up to that one. And whenever you see it's a curve between 0 and 1, and whenever you see that there's a rise in the curve, actually there you have in the bridge admittance like a noticeable amount of energy which is concentrated. And you can see that typically what happens is that the amount, let's say the greater increase in the curve is towards the bridgeal. So that's a good way to find where the bridgeal is placed. and the curve can be used and compressed in a let's say more compact representation just using some parameters. And here there are some of them. We fitted the curve with a this S-shaped curve right here that you can see, and this can be explained with very few parameters, which are the starting point of the curve, which is the relative power amount at the end of the signature modes. We have like the position, the Brigil central frequency, which is the position with the maximum slope of the curve. We have its amount. We have the curvature. This K star is the amount of curvature of let's say S shapiness that you can have in this curve, and then you have also the decay slope of the eye frequency. So a bunch of numbers that can somehow summarize what this curve can say to us. And the idea of collecting these few parameters, quantitative parameter, is to try to collect this data set of bridge admittances and look at a few numbers to see if there are similarities or divergences. But actually, now we have this kind of collection of data, but then how to deal with them. And so I thought to share with you two different experiences in which we tried two different approaches. Um, the problem with violins is that there's a lot of variation. So one can vary the arching, the can use different molds, and so also the plates has different dimension. The airfoils can be shaped in and placed on the plate depending on the arching. The rib can have different height. We can use bridges with different adjustments and so on. So it's very difficult to somehow correlate some of these parameters to what happens in the bridge admittance. So how to deal scientifically with that? The easiest way is to find a control case scenario in which you have an experiment in which you can reduce any source of variability, maybe stick to the same violin, maybe stick to the same setup, and then be sure that you are changing one variable at a time. And in this case, you have the possibility to try different things. For example, this allows you to control also the variation. Maybe you can do stepped variations and measure the bridge admittance anytime of this at any step of this control variation, and then check if the bridge admittance has a coherent evolution depending on this parameter. It becomes easier to infer something significant, the impact of this variation on the bridge admittance. Otherwise, if you have a collection of data like mine, collected over the years, but you know that the experimental procedure is the same, it's difficult to find a one-to-one relation between how you design the violin and how you measure and what kind of bridge admittance you expect to measure. But at least you can try to use some statistical analysis, data analysis oriented approach if you have enough violin to check if there are correlations, to check if you can somehow sort out the data and find something interesting. And so the first experience I want to share to you is like the first approach. So trying an experiment in which you are sure that you can control one variable. For that, I met some months ago a guy, Ruggero Cortese, which was a student of the School of Luteri of Milan. which went to the lab one day to ask if he could do an experiment of violin bridge adjustments. And that was the first time to me in which I understood, since like an engineer, I'm not that, my background, let's say in violin making, is still like building up. Uh, they started from scratch, and then I started like collecting terminology, understanding what can be done on a violin. That was the first time to gather like sort of background on bridge adjustments. And the first step with Ruggiero was exploring what means adjustments, what we can do on bridges. Actually, there's never thought about that, but there's a lot of parameters that you can actually modify also in a bridge. And so the first thing to do using the first approach is, okay, let's isolate one and decide one. Here in the picture you can find like a scheme in which we I put all the parameters that I collected looking at the literature, at the background, and all the min and max values that violin makers typically use. Actually, they are somehow, that's a draft, so I think that there could be exception to it. But the first thing I thought, also considering some background studies, I think, for example, the one of Jim Woodhouse about like modeling the bridge as a mass spring system, is trying to find, for example, one of these parameters that can change the rigidity, the actual rigidity of the bridge. And so we decided to go on the waist width, which is the one that I highlighted in the picture. And the idea was, okay, why not trying to reduce the width of the waist in a gradual manner, just half a millimeter by half millimeter, and every time let's measure the bridge admittance and see if something happens, if the bridge admittance changes. The idea was, so varying these parameters and understanding what we would do to reduce all the uncertainties. So the idea was, let's have the same violin. Let's every time take out our bridge, do the adjustment, put again the bridge on the violin, tune the violin, and so on. Actually, it was the patience of Ruggiero's patience was very like an example for me, because actually he did this like several times, again and again, and it was very methodic in doing that. But we decided, why trying just one bridge? Let's do multiple times and see if we can have a coherent behavior. So we started from 4 violin bridges blanks, taken from the same provider, made of maple wood, almost same weight, about 2.8 grams. During the experiments, we took these bridges, we mounted them on the same violin to the 44 hertz with the help of a string lifter. And then we started doing the experiment. Actually, before starting the variation of the waist width, we asked ourselves one question, which was, I never tried it, so I was interested to do it. What happens every time we take out the bridge and we put the bridge again? Like we are changing the strings, or we are doing just adjustments, but without modifying the shape of the bridge. So just keeping out and keeping in. So we tried it. We use the string lifter. We just do it for the 4 bridges under test 3 times. We take out and put it again, and we measure the bridge admittance. the idea was to understand if the bridge admittance is a stable and robust measurement against these kind of uncertainties. So Ruggiero was very careful in replacing the bridge, taking out and putting it again. But actually, you have always a bit of uncertainty in where to put the exactly the feet position, and so on. This was the result. Here you can see the curves. The curves uh, are actually like the free curves for the four bridges. So free repetition for each bridge, for each of the four bridge, and the color shade or the color region that you see there is the statistic. So it's the mean plus minus the standard deviation. And so the first thing that I noticed that it was that actually that's a good amount of uncertainty. So the for each of the bridge, the region, the window of uncertainty represented by the standard deviation is quite constant and limited. Somehow representing that the way we measure things is not too much uncertain. We can do something. Actually, this kind of uncertainty is like the starting point because if with the variations that we will do are not changing the curve outside of these regions, this means that the parameter we are changing is not relevant for the sound of the violin. The second things I noticed is that in this case, the four bridges, which are taken by the same provider, same material, similar weight, they are behaving in a very coherent way. So that was a good starting point. And actually, we quantitatively consider this uncertainty because this will be the measurement error that we will face when looking at the final results. The second experiment was okay, we have these blanks. We try to put in the violin, take out and put in again to have the uncertainty of the measurement. Let's try now to vary the waist width. So we do different steps. We start from the original width of the blanks, which was 17.6 millimeters, and we start with a step of millimeter of reduction, which means alpha millimeter from each side. At each step of reduction, we did the bridge admittance again, we measure it, and we collected all the evolution of the bridge admittance throughout the process. This was done for each of the four bridges. So what we obtained at the end was graphs of this sort, which you see the gray colored area, which is the original blank without the waist width variation, but with the uncertainty of the taking in, putting in again, taking out, putting in again experiment that we did. And then from light blue to dark blue, you see the bridge admittance variation after each step of the adjustment. And what we saw looking at the bridges, then we will go through the four bridges, is that the like more noticeable variation was around 2 kHz, in which we had this reduction of the bridge admittance, which means that that specific area of the frequency range we have a reduced vibration. And this reduced vibration keeps to be reduced with the waist of the bridge being thinner and thinner. And we looked at the bridge B and we obtained coherent behavior. Bridge C was somehow a sort of outlier in the sense that it was more difficult to see this decrease in the amplitude of the bridge admittance along the steps. at least all around 2 kHz. There are some places, for example, just below 2 kHz in which the variation is still coherent, but then above 2 kHz things becomes a bit messy. And then we had bridge D, in which again the reduction of the amplitude in the bridge admittance around 2 kHz was quite noticeable. And to be sure, we tried to check all the bands, so different frequency ranges along the bridge admittance. Here you see that this is the mean and the standard deviation of the variation of the bridge admittance while reducing the waist width. Zero is exactly the means that the variation is none, and then plus minus 6 and minus 6 are the variations. Typically, since we are looking at a reduction, we are looking at the negative values. But I've also put these red dotted lines horizontal, which are actually the measurement uncertainty that we found from experiment 1. So actually, all the bands, all the frequency ranges are still inside this interval made by the measurement uncertainty, except for the band around 2 kHz, in which we see a reduction and a decrease, while the parameter of the waist width is decreasing and reducing. And for very low values, which are like 13.6 and 12.6 millimeters, the variation is going outside the curve, so the outside the window of uncertainty of the measurement. So it's becoming somehow, there's a trend that is becoming somehow interesting. And this is a way to summarize this kind of result. And the possible interpretation that we thought about is what happens around 2 kHz. We didn't check actually. We could have tried to look at the resonances of the bridges. We didn't do that, but our hint on that is that reducing, of course, the waist width, we are making the bridge less rigid in its rocking motion. And typically to around 2 kHz, we have the resonant frequency of the rocking motion mode of the bridge, which was expected somehow. So it was good to see it, and it's somehow a confirmation that trying to do experiments in this way in which we can control everything and try to vary just one parameter at a time, it's a good way to find a relationship and check hypotheses and see clearer relation between construction parameters, adjustments, and what happens to the vibration of the instrument. Then there's the second approach, which is more related to the collaboration that I had with Museo del Violino, with the UNESCO office in Cremona, because in this case we are more organizing events and dissemination for violin makers, in which we give the possibility to measure their instruments, or we try to do a bit of historical research about how the Cremonese violin making was changing from the beginning, from the 17th century until today. And so the idea is to gather a lot of data and try to make sense of them. And so in this case, we are in the other approach, which is trying to do a bit of data analysis on a collection of data, which is varying alongside many variables. So the context is, as I was saying, the UNESCO Safeguard Plan. It's a set of activities that are made throughout the year which are dedicated to the target. The target public can be actually anyone. There are some activities, dissemination activities for musicians, some dissemination activities for violin makers, some for just citizens interested in the topic. And in this case, what I want to share with you is the results about an historical research that we did for dissemination dedicated to violin makers in the Museo del Violino. And I just come back to the graph before. If I want to see this picture and try to be more with the point of view of a data analyst, then the idea is to try to answer this kind of question. So if I'm able to discriminate between violins, if I can say how much two violins are similar, and essentially definitely if I can find correlations between different parameters and what's going on in the measurements that I collected, which are more things related about statistical analysis, correlations, similarity, sensitivity analysis, something that is very familiar to data analysts and engineers. So the idea was to check the collection of the violins that we had. This is somehow summary of the violins that we collected and used for this kind of dissemination. We had some historical violins from the collection of Museo del Violino, which are from Amati and Stradivari and Guarnieri. They are dated back to the 16th and 17th century. Then we had a subset of violins which were dated back to the 18th century until 1937. I will explain after why 1937 is a time limit that is considered here in the groupings. And then from 16 violins from 1937 until today, most of them which were winners of an international competition that is held by Museo del Violino and some institutions in Cremona, in which violin makers join the competition and makes these violins, which are following a specific set of rules, which are considered very similar to the ones that violin makers agreed as the Cremonese style, trying to emulate what the old masters were doing. This was the collection of violins, and from these violins, not only the bridge admittance was collected, but I had the chance also to collect an entire set of dimensions, in particular the dimensions of the plate, of the top and the back plate, the length, the width in different locations, the height of the ribs in different locations, in 3 different locations, and also some informations about the F-holes, the vertical position of the F-holes with respect to the length of the plate, the distance between the holes in different positions, so up, mid, and down, and the length of the right and the length of the left hole, as you can see in the diagram. Actually, we didn't measure the arching, but somehow the measurements that we collected from that we acquired from the F-holes are somehow giving us some hints on the arching of the violin. And so the first thing I tried to do was, instead of starting from the bridge admittances, let's see these dimensions of the violin box and trying to do some statistical analysis. Here you can see a graph in which I put the different dimensions from A to labeled from A to Q, and also like some estimations of the aspect ratio between the plate length and width, and the unexpected estimation of the volume of the violin body. And the colors are just telling us how much far from the average dimensions these dimensions are. So when the dimension is colored as white is towards zero, this means that the specific violin has that specific dimension very similar to the average among all the violins in the collection. When the one violin has one of these dimensions very far from the average of the total collection, if the dimension is quite high, then it becomes red, and if it's quite low, it becomes its color in blue. So here you can see the each row is one violin, and so these are collected in chronological order. I put them in chronological order because the first way I tried to analyze the violins was to group them by violin makers. Since I had a set of Stradivari violins from the collection of the museum, I said, why not putting them together? But the first thing we notice is that things changed over time, and this graph somehow can be interpreted in this way. If you look at the first part of the graph, you can see a lot of blue and red, which means a lot of variation. Between the 16th and the 17th century, there was, according to the violins we measured, and they are collected by the museum, there was different models, starting from small violins in the 16th century, and then towards bigger violins in the 17th century. And even the same violin maker, Stradivari, for example, changed over time the shape. Then in the 18th century, things became different. You can see a lot of red, and Cremonese violin makers decided to do bigger violins, bigger in general. So the trend was to increase the volume, to increase the dimensions, to probably to have more volume generated by the violins, maybe because they were used in orchestras and not anymore in musical a camera. After 1937, actually things becomes lighter, very towards white. The interpretation here was after 1937 in Cremona, they started studying again Stradivari and Amati and ancient masters, and so they decided to keep them as references while doing their violins, and so things are becoming more, let's say, more respect conservative with respect to the models. Less variation, everything is more is varying less, and this is somehow the evolution of Cremonese of the Cremonese violin maker over a year. That was quite interesting to see. Actually, what was varying a lot inside this collection of violins was the position of the F-holes, and in particular the distance between the holes. Here I put this graph in which there is the relative variation of each of the parameters with respect to the average. On the left, there are the parameters that are varying the most in the collection of violins I had, and in the right, you see the parameters that are varying the less. And so the F-holes and their variation was quite noticeable with respect to the other parameters. And so was the first aspect that I wanted to check then after measuring the violins. What about the measurements? So I did the measurements, and also I grouped the violins with respect to the historical period, and I checked at how the bridge admittance was varying over time. And actually, something was confirming the trend that I was explaining just by looking at the dimensions of the violin body of these violins. In green, you can see the reference, which was the 17th century. I decided that because the 17th century is somehow the golden age of Stradivari, so it was interesting to keep just a comparison with a common reference along the evolution. And in the 16th century, we see that the bridge admittance in red has this deep in around 2 kilohertz and 2 kilohertz and a half. While in the 17th century, there's actually the Brigil in that position. In the 18th century, the blue curve, you can see a response which is on average quite flat and very similar to the green one in the high frequency. But then in the 19th century, you can see around 2 kilohertz that something is trying to resemble the green curve. So the violet curve, which are the violins in the first half of the 19th century, starts resembling the shape of the bridge admittance of the 17th century, and while modern violins from the 1970 up to now, they have this clear bridge yield around on average around 2 kilohertz and a half, with a very similar decay in the high frequency and a very similar amount of energy in the signature modes. This is the relative power curves that we compute in the groupings that we made. Same colors are denoting the same historical periods, and you can see, as always, the green curve is our reference, the 17th century, so the Stradivari Golden Age period, and you can see that while time is evolving, also the violins are somehow starting. We had one time, 16th and 17th century, in which we had a lot of variability. In the 18th century, we had a specific way of doing the violins, bigger with respect to the models of the 17th century. But then in the 19th century, we started at similar trends with respect to the models of Stradivari, of Amati, and so on. What I was interesting was to search for some correlations, not only between construction parameters and bridge admittances, but also between construction parameters and construction parameters. What I just tried here, you can see a correlation metrics. Correlation means how much a parameter changes because another one is changing. They are linked by a relationship, a linear relationship, so a proportion. And the Pearson correlation coefficient is a measure, a quantitative measure of this kind of relationship. So the higher the Pearson correlation coefficient, this means that the dependency between the two construction parameters is strong. In particular, above 0.6 up to 1, so for darker colors you can see like stronger dependencies. And what was interesting was that all the parameters, construction parameters related to the plate dimensions, of course, are linked together because they depend on the chosen shape. So depending on the chosen shape, these are proportionally, let's say, correlated. While the height of the ribs is independent from any other parameter. And then we have the position of the holes, which depends not only on the shape of the hole, so the distance and the length of the holes, but also on the dimensions of the plate, of course, because depending on how much the plate is wide or narrow, also the distance between holes changes accordingly. But then I did the same thing, so I tried some correlations between the construction parameters and the vibration descriptors that I explained before. doing the same thing. So measuring the Pearson correlation coefficient. Along the rows, you can see the construction parameters, and along the columns, you can see all the bridge admittance descriptors that I extracted. So the first part of the columns are the frequency, amplitude, and Q factor of the signature modes. While on the second part of the columns, you can see all the descriptors related to the relative power curve. So they give especially information about where the bridge yield is placed and how much energy is involved in that frequency range. And here you can see that the matrix is quite wide, except for the rows which are related to the parameters that are describing the FOs. So one question was maybe the FOs, which also hide somehow information about the arching of the violins, if we change how they are placed and the shape of the FOs, maybe we can have an impact on the bridge admittance. Actually, we try a look each of the relationship between each pair of parameters, and what I found is the very interesting thing that I found was about the dependency between the distance between holes and hole length with respect to the position and the amount of energy in the bridge yield. And in the specific case, these are I just tried to select which ones were actually resembling a line, so there was strong correlation, and which were not resembling a line. So with very low correlation value and linear regression that was not fitting well. And actually, I found this. It was a tentative way just to sorting out things, so I don't take them as much serious as clear rules to state something about the bridge admittance and the parameters, but somehow it was quite interesting to look at which kind of relationship there was between the bridge admittance and each of the parameters. For example, here you see that one of the strongest correlation was about the distance between the holes along the width of the plate, and the energy in the low frequencies and the energy in the bridge yield. And in particular, if we increase the distance between the holes, in particular in the upper part of the holes, the relationship in the bridge admittances seemed to be less energy in the low frequency and more energy around the bridge yield. And another one was what happens if we shorten or we lengthen the FOs along their diagonal. The correlations that I found doing this kind of method was if you increase the length of the hole of the FOs, you increase the energy in the low frequency, and you decrease the central frequency of the bridge yield, but also you decrease the amount of energy in the bridge yield, and you put more energy in the high frequency, and so you have a decay of the bridge yield around 4 kilohertz, which is flatter. And in this way, these are dimensional on the bottom of the slides. You can see dimensional plots. So actually, I had the possibility also to give a rate of the decreasing trend and the increasing trend for each of these pair of bridge admittance features and construction parameters, such as like some sort of simple rules to remember. If I do this, I can see this in the measurement. So it was a tentative way to somehow sorting out things in the mess of the collection of the violins that I had, and two interesting things were actually I was collecting from this experience, which were I worked with the curator of the museum, so I had the chance also to know a bit about the history of Cremonese violin making, and actually the literature says that 16th and 17th centuries in Cremona were a very, let's say, golden period for violin making, which there was a lot of experimentation where the violin became the violin as we know. But then in Cremona, after starting from the 18th century, we lose all the tradition, we lose the knowledge about past violin making. We do a different way of we use they used a different approach in making violins, and we have to wait just until 1937 when Stradivari's model were began to be studied and were taken as a reference. And 1937 is a time indicator because actually it was the year of the foundation of the first school of violin making in Cremona. In that period, people like Fiorini and Mosconi started keeping Stradivari back to the city of Cremona, and they started studying them, understanding the designing method and the shape used by Stradivari, and they started to use it as model as reference. And then there was the second, let's say, interesting thing of this approach of trying to sorting out things from the collection of data was that some interesting correlation can be somehow found or at least highlighted by doing some statistical analysis on the data. But it was just tentative preliminary. So this kind of correlation needs more violence. So a huge amount of data to confirm what we saw, and then I still think that the approach of trying to do controlled experiments in which we can just vary one parameter at a time is the best scientific way to try to understand if there are some specific impacts caused by construction parameters and influencing the bridge admittance. So yeah, just the idea was just to share this experience and these two kind of approaches that I experienced through the years. And if you have any questions, I'm here glad to answer them. Thank you.
All right. Thank you very much, Rafa. That was very interesting. And if you have questions, please use the raise hand function. In my app, it's under the React panel. So if you can't find it, or you can always just send a message in the chat that you want to be recognized. So questions. Hmm. Well, Joseph is clapping. Great presentation. Joseph, do you have anything you want to ask? Oh, Jim Ham. Unmute yourself.
Okay, am I unmuted?
Yes, we can hear you.
Okay, yes. Thank you for this excellent presentation. Um, I'm wondering when you did the four different bridges that were modified in shape, if you also just put the same bridge, took it off and put it back on and tested it to see how much variation you would get with no other change.
Yeah. That's let's say first test we did. Actually, because I wanted to check if like our measurement rig seemed robust or not, and I can also show you that there was first experiment we did, the idea was I asked Ruggero to use the string lifter, take out, put the bridge blank on the violin. We measure the bridge admittance. We take out the bridge and we put it back, and we measure again the bridge admittance, and this is the results. So like the colored regions that you see here are the four, it's the uncertainty as a function of frequency for each of the four bridges. On average, it was about 2 decibel in the
Yeah,
in
so
the
I think I see that the thickness of each color band is how much difference it makes just to take the bridge off and put it back on.
Exactly. Yeah. Yeah. Yeah.
Thank you.
And we use it because actually then when I looked at the bridge admittance with the variation, I considered the variation to be null, like the impact of the variation to be null whenever the curve was superimposed with this kind of thicker curve, which was the uncertainty of. So in this case, for example, if I look at the low frequencies of the bridge admittances, my conclusion was changing the width of the waist was not affecting the bridge admittance, at least not as different as just taking out the bridge and putting it back. That was the my idea. That's why then I thought, okay, around 2 kilohertz, something is happening actually, because we are far from just the uncertainty of the measurement or just the uncertainty of playing with the bridge without changes.
Great. Thank you.
Joseph, you muted.
Thank you, Raphael. I really enjoyed that talk. The slide you're at, what surprises me, well, first of all, these curves haven't been normalized, have they? Or
No, no,
they're
no, they are.
as measured. Okay. So I would expect the slope going down to change quite consistently with narrowing the bridge waist, and yet it doesn't seem to change at all.
Yeah, yeah, that's interesting. Yes. Actually, I'm not sure about that. It's just my interpretation. I think it's because of the um, parameter chosen to be varied, in the sense that somehow I expected that changing the width of the waist was affecting uh, that specific frequency range around 2 kilohertz, because probably these blanks are have a very let's say huge weight with respect to the average of violin bridges, because wood was not removed still. So I expect there to have like the resonant frequency of the rocking motion of the bridge. So I think that changing that parameters is just affecting that and not affecting the rest of the let's say of the transmission of energy throughout the bridge to the violin box.
How heavy were the bridges on average?
It was 2.8 grams. So it was just
Oh,
taking the bridge blanks with all the weight of the wood and just changing the that parameter actually.
so to clarify, the bridge planks were not cut to final typical final dimensions.
Yeah, exactly. Yeah, exactly.
Oh,
That was the thing. So actually, that was a really like preliminary experiment. So the idea is to next take the bridges, so still an amount of like 4 or 5, which is statistically significant. Adjust them until like the final steps, and then doing this kind of variation, because then the removal of wood becomes more significant in terms of like weight change.
And um, you don't reference at all Jim Woodhouse's bridge theory. I mean, we know what to expect, and that's, I think, pretty robust. And I'm trying to see how it fits on this, and it. So the first thing is the slope isn't changing. The weight, if you say they're that heavy, then I imagine that the rocking frequencies are rather low to start with. I'm guessing that for that's my guess, but that would have been good to know. But
Yeah.
I think this has been much studied and much understood. What are you trying to find out apart from preliminary investigations?
Yeah. Actually, it was just so the idea was to find a way to, um, I mean, just have a preliminary test on how to do a good experiment without changing too much and just varying one parameter and see if what you what is expected is actually easier to find with respect to like changing instrument, changing different other different parameters in the experimental setup and so on.
Okay, fair enough. The other thing is, um, in the photograph, the bridge foot position doesn't seem to be marked, which I would think would definitely make it hard to put it back in the same place every time. Or am I missing something? Were there marks there?
Not in this case, but actually, Ruggiero was supported by the string lifter. So actually, putting the string lifter just after the bridge was a way to uh, like keep in store the position of the bridge while doing the measurements.
Okay. Well, thank you. Thank you.
Any other questions? So if there are no other questions, I have a question, which is um, what types of investigations are you thinking about doing next?
So, yeah, that's a good question, actually, because so the idea of taking this like preliminary test on bridges was to find like a good protocol to do this kind of investigation. And then the next idea would be to like experimentally try to do the same experiment just by varying one parameter at a time. Um, so to compare then the results with the literature, as also Joseph said, there are some models about like the behavior of the bridge on the violins. Jim Woodhouse did a lot on that, and so the idea would be to like collect experimental data in a fair way to then compare the results with what the literature says about also like models, uh, mathematical models, theoretical models, and so on. For what considers specifically bridge adjustments and also adjustment in general on the fine tuning of the instrument. While on the other end, regarding the collection of violins that we have, I think that the analysis that we did was very limited in the dimensions that we collected. For example, here we don't have any information about the arching, which is quite that gives a lot of impact in violins, and that is very a topic to discuss with violin makers because many times we talk about how the arching changes, and there's a lot of parameters that are considered when arching is involved. But also there's no information about materials here, so it would be nice also to extend this kind of analysis also to understanding what kind of materials are used. We did this I acquired this collection of violins with also varying like bridges, strings, so also that kind of factors are adding a lot of variability in the data, so they are a bit generating noise in the correlations that I try to highlight. So probably try to find a way also to add more informations in the collection of data that I have to clean a bit the correlations that I found and to try to confirm them.
All right. George.
Hi, Raffaele. Thank you for your presentation. Question about your bridge blanks that you use. They were about 2.8 grams uncut uh, before you worked on things. What brand were they or model were they? I'm curious.
So actually, I have to admit that I'm not sure about that, about the supplier, because Ruggero did like the furniture. I can confirm that they were 2.8 grams uncut,
Okay.
and so we started with them. Um,
That's kind of light. That's why I was curious. I've come across bridge blanks that were much heavier.
hmm, I think they were some sort of like they were the same shape, so I think they were just like a default starting cut where to just where to do adjustments. I mean,
So the 2.8 grams was about the weight that you did the measurements on.
yeah, yeah,
Okay, so it sounds like that they were sort of cut to a certain extent, from the
But to
yeah,
a
bridge
tiny
exactly.
blanks.
extent in terms of narrowing the waist. But if you're starting with, say, 17 or 16 and a half across the waist and having a bridge blank like that, in my own experience, that's an awfully light bridge blank. And I like light and stiff bridge blanks. So that's why I'm asking the question, what supplier did you have or what manufacturer did you have for those light?
There's a good question actually. So
So I
I
mean,
will check it. I will check it. If I know,
yeah.
I will share to you.
Yeah, please. I'm curious.
If I could just add to that, if that actually is what you were measuring with, then a huge part of the mass is at the top of the bridge where it's most going to affect the tuning. So
Hmm.
I do think it takes it down into an unrealistic range of tuning. But as you said, this was a preliminary experiment,
Yeah.
and you very much illustrated what you sought to illustrate.
Mhm. Okay.
Thank you,
David.
Rafael.
Wait, George. Oh, okay, you're done. All right, David.
Oh, yeah, me. Yeah. More a comment than a question, but one of the things I love about acoustics of musical instruments, I'm an amateur. I'm neither a good professional researcher nor a builder. But when you talk about changing one parameter at a time, that's always very ambiguous, actually. So you talked about the positions of the holes at the ends of the F holes. Okay, I know two things from Helmholtz. That's a while ago. Zeroth approximation. If you have a hole in a baffle and a pressure difference between the two sides, the airflow surprisingly depends on the circumference for the same shape. Also, from Helmholtz, the resonance of the air in and out depends on the area. And then I learned from Jim Woodhouse, other people knew it, that the uh, shape, the whole geometry of the F holes affect the oscillation of the
Island area.
soundboard. I forgot what it's called, under the bridge. So you change one dimension and you're getting into all these physics effects.
Yeah, yeah, yeah,
It's the way
indeed.
it is.
Yeah.
And it's kind of great that way because that just suggests a zillion other experiments. Because when you change one dimension, can you now compare ones with the same circumference? Can you? But that change, ones with the same area with that change, is that a reasonable thing to do? I don't know. Anyway, it's always, for me, it's just fun. But
If I could just interject, another thing about Helmholtz, I think, is affected by the flexibility of that opening. So, how thick or thin are your plates around the F holes? How flexible is it?
yeah, that
That
was my third one. Just the motion of anything you change in the construction will change the, if you will, the frequency of and amplitude of motion of that region, which is crucial to the bridge hill, etc. But these other ones, I don't know. What I described are really the zeroth approximation um, which is to say, I know the derivations in some very simplified geometry, and whether that's at all relevant over the range of variation that you have, I don't know. But at least some people have thought so about the evolution of sound holes coming up to the era of Stradivari, right? They're round ones, they're two crescents, they're in different places. And
Yeah,
anyway,
yeah, right. I agree with that actually. The collection of the construction parameters were made by like the violin makers that attended this kind of dissemination. So actually, that was then like when we did the discussion about the results, that was actually the case. I mean, we all recognize that the set of parameters that we collected was not actually representing all the parameters at play. I mean, they understood that like checking the efforts in this way means including in these effort parameters like how they did the arching, how they which was the as you said, like the length of the contour line of the apples, the area, thicknesses are not included here. And so, yeah, actually looking at the correlations was I tried and fit, let's say, a line on some measurements which are probably hiding um, more and more complex like relationships with hidden parameters that we didn't observe when we did the this kind of analysis. So yeah, that was a lesson learned during during the research.
All right. Anders?
Yes. Um, Thank you for an interesting talk, and seems to be a good laboratory you work at. Are you using a laser vibrometer for the admittance tests?
No, in this case, we use an accelerometer. So we did
Okay.
just the bridge admittance along the sides of the bridge with an
Okay.
accelerometer.
I wonder, you showed some special graphs with the different area violins and responses, where they seem to divide quite a bit for different times. And I wonder, are there any Baroque bridges on any of those instruments you tested, or is it modern bridges on all of them?
No, yeah, I would say if I remember well, it was always modern bridges, also in historical ones.
Okay.
There were no violins set up in with the Baroque approach.
Okay. How many instruments are there in the study, in the statistical study?
The statistical study, the one with dimensions, was about 30.
Okay. Thank you.
Right.
Good luck with the work, further work.
Thank you.
Another comment was that in the correlations you saw from was it 70 violin study, the distance between the F holes and the length of the F holes you showed was doing something. Is that right?
I mean, it seems like a correlation which was more robust than like the other relationships.
Yeah, which suggests to me we're actually, I mean, at the Oberlin Acoustics, kind of the group and the workshops, we've been fairly systematically studying first the bridge, been going along with Jim's theory, and then the sound post and the bass bar. And some obvious next questions are, um, how does the proximity of the upper holes of the F hole change things, and also how does the length of the F hole change? So I don't know if you have makers willing to be involved in that, perhaps some kind of collaboration so we can answer the questions that are quite tightly focused on what makers do and can change. So if there's any possibilities of that, I would love to talk more.
Yeah, yeah. I mean, I would like to. I think like in the last years, I think like violin makers are more willing to try to do experiments because they
Hmm.
want to know. Also, like in the Cremonese context, especially. I mean, I know that kind of experience, which was maybe less prone to do that. But now I think there are more like people that want to be involved in these kind of things. So there will be the opportunity, of course. And yeah, as you said, like so these kind of correlations are really related to like the island region. There's a lot of papers made by also most of you also here in participating, um, talking about what happens if like the island region is wider, is narrower, and so on. And I think these kind of like correlations are going towards that kind of interpretation. And yeah, I think that as we were talking before, changing one parameter, for example, like just like the height of the arching, is changing the rotation of the effals, maybe is changing so the distance between them, not only like maybe in the upper side, but not in the middle and in the bottom side. Um, and so yeah, the idea was okay, if we use the first approach in this case, you should have like you should set up like a violin box, but you should have been able to somehow gradually change the shape of the effals while performing the measurements. Uh, Actually, I'm not a violin maker, so I'm not sure how it is easy to do that or not. But yeah, if someone was would be willing to do that, to try it and see if something reasonable happens, I would be glad to join and support.
Well, those experiments with real violins tend to be punishingly time consuming, and I know because we tried to find out what we can really learn in a week, and we can, but you have to be incredibly focused and prepare the experiments ahead of time. But a couple of thoughts come to mind. One is, are violin makers interested? I would say yes, especially young ones, because I get a fair bit of correspondence from young makers for a school thesis or even a PhD with measurement projects asking questions. And um, my overall sense is that a lot of them are removed from where research is now and going at things like tailpiece length or fingerboard, things that are questions to makers, and they can then spend months or years working on them. It'd be great if there's some sort of, I don't think it's possible, but an international reference for what we know, what we don't know, and kind of um, interesting questions that are answerable mainly by violin makers doing careful work. Um, anyway, but I do think and as evidenced by the maker who did your bridges, that someone could sit down, the kind of patience and rigor it takes to do that is very admirable, and that's to have 8 people like that in a room is fantastic.
Okay, any other questions? Well, if not, let's
Well,
give
let me just ask one.
Yeah.
Raphael, what are your personal goals? Are you interested in following violin research, or is it just one of many areas that you're involved with?
So up to now, it became so as a PhD student is one of the like the main topics. Actually, now with the uh, like with the new job as technician in the labs, I'm more involved in an heterogeneous, let's say, set of activities. So it's becoming harder to focus on violins. But actually, what I think is my goal up to now is to like maintain the collaboration with the museum because I think it's like really part of the texture of networking that is in the city and so like going on with the UNESCO safeguard plan and trying to collaborate with museum to do dissemination and trying to do this kind of research. Also, if the process is slow, to be more and more scientific, but also more and more involving like musicians and violin makers too, because sometimes the terminology is very different, and also the way we look at things is very different. For example, we did a perceptual test in which we put bridge admittances that we measured, and we tried to compare like the violins. But if you talk with a musician, like his main focus is about like the playability sometimes. Uh, and so maybe a violin maker did some choices, but the musician finds more relevant to talk about how maybe the fingerboard is made because not able to play at the end uh, of the fingerboards on the strings. And on the other end, if you talk with the violin makers, sometimes like um, they focus a lot on specific elements, because while making the violins, they were the focus, their focus, uh, like in the process of making a violin, but maybe they are not. Also, like I think I just repressed what you said before. Like yeah, but I think like Jim Woodhouse is doing it, like writing the book of the euphonics book, like having a reference in which we like grow and we put all the things that are relevant and which are not, and um, like a common terminology, a common way of looking at things and interpreting things while doing this kind of research is like a crucial step, I think, in general.
Yeah, it's almost like a study guide to euphonics for violin makers, which narrows in on the appropriate parts, but also gives some really basic um, um, connections. Um, but tell me, do they teach acoustics at the violin making school? Is there that a formal element of the program, or do you just get occasional interest makers?
No, I think it's like occasional dissemination. So sometimes we are like invited as guests to do some like fundamentals of acoustics in like seminars in during the course.
Hmm.
Up to now, I think it's very like dedicated to how to make things, uh, to the making techniques more than like a comprehensive study of everything.
Okay. And is
But
it
they, with respect to some years ago, it's like better the situations. I mean, the thing are like going towards like a more comprehensive like dissemination of things. Also understanding a bit of acoustics, understanding a bit of materials, understanding a bit of making techniques more heterogeneous and comprehensive.
Mhm. Well, thank you again for giving us your time and
Yeah,
your
let's give
research.
Raphael a great round of
Thank you. Thank you very
applause.
much.
And thank you very much for this wonderful presentation. So